Next, we will look at closed domain methods. And like I said earlier, these methods are based on bracketing a root and then refining that bracket until we hit the root. And the first method we will look at is one of the simplest root finding methods called the bisection method. And as the name suggests, we start with a bracket, an interval that brackets a root, and then bisect that interval in half. And then choose a new interval where we're sure that the root lies in there, and then keep refining and refining until we hit the root. If you remember early on in the course, I gave you the example of iterative methods with the dictionary trying to find the page number for the letter M, where you took the dictionary, cut it in half, and then you started taking either half and then taking the other half as well, and so on and so forth until you hit the root. This is called the bisection method. Okay, so let's start with a graphical example. Take this function, this curve shown here in blue. Let's start with a and b that bracket the root of f of x. In this case, this root is around 6.75, like we've seen here earlier. So we're going to pick a and b such that they bracket the root. Now, the next step is to find the midpoint between a and b, and that's given by c equal a plus b over 2. And visually, c is located over here. Now it's time to update the interval. We have a new interval that brackets the root, and that's going to be c and b. So we're going to rename those. C is going to become the new a, and b is going to remain the same. And then we do the same thing again, or we check for convergence first. Is f of c equal to 0? Is it less than a tolerance? Otherwise, keep repeating. Now, convergence in this case is simple because all you have to do is check if f of x or f of the root is equal to 0. Okay. Otherwise, repeat. In this case, we're going to repeat. Take again the midpoint between 6 and 9. So that's 6 plus 9 over 2 equals 7.5, and so on and so forth. And now C becomes the new B, so you got to find what side you're on, and C becomes the new B, and then A and B, and then you cut in half, and so on and so forth. The bisection method algorithm is simple and is given by these 3 steps. Given A and B, which bracket the root, then set C equal A plus B over 2, choose new values of A and B, and the way you do this, you want to figure out whether you're on the left side of the root or on the right side. Remember, the way these roots are given, we follow the assumption that A is to the left of the root and B is to the right of the root. And so if f of A times f of B is negative, then we know that there's a change of sign between f of A and f of C. Sorry, if f of A and f of C multiplied by f of C is negative, then we know that A and C are located at different sides of the root. So since A is to the left, then the new B is going to be the C value, and that's going to be our new interval. Otherwise, leave things, otherwise A becomes C. Then check for convergence. If converged, return C or A plus B over 2, otherwise continue. Okay, so again, f of A times f of C tells us whether C brackets the root from the left side or the right side. Okay. Now, convergence is close enough, is saying that f of x is close enough to 0. So we can do this in 2 ways. The simplest way is to just check if f of c is less than a certain tolerance, but you got to be cognizant of the size of f. So, for example, if f varies from 0 to 10,000, then a tolerance of 10 may be sufficient. But if x varies from 0 to 10 to the minus 3, then you may require a tolerance 10 to the minus 6. Another way is to do a relative tolerance and keep track of the roots and check if you're making any improvement on the root. Okay. In terms of turning this into Python, I'm asking you to do this little activity here. If you were to write a Python routine to implement the bisection method, what would you choose as inputs and outputs for that routine? Remember, the way I like to describe Python routines is as functions or routines that take in certain input and provide a certain output. So think of a routine, what you'd want from a routine for the bisection method. So the routine at a minimum requires the following. It requires the function name, for which we want to find the root, the initial root bracket A and B, a tolerance that tells us when to stop, a maximum number of iterations because we don't want to keep trying to find the root. What if there's no root? We don't want to keep looping forever, otherwise it will lock up the system. The function would also return, the routine would return the following: the root itself, the error, optional, and the iteration count needed to find the root. And I'm showing you here a pseudocode, or actually a Python code that implements the bisection method. And as you can see, it's called bisect, and define bisect takes f, any Python function f, such that f is f of x. And a and b, these are the brackets of the root, a tolerance, and the maximum number of iterations. We start by defining a very large error, so I take the tolerance, add 100 to it, starting with a counter for the number of iterations equal to 0. And as long as my error is greater than the tolerance and the number of iterations is less than the maximum iterations, let's first augment the number of iterations because that will be our first iteration, and then define c is a plus b over 2, and then check if f of a times f of c is negative. This means that because a is to the left side of the root, then if f of c is opposite sign of f of a, then it means that c is to the right-hand side of the root, and therefore the new interval a remains a and b becomes c. Otherwise, a is our new c and b remains b. And then calculate the error, f is absolute value of f of c, and then return the root itself, the error, and the number of iterations. Okay. Before we get to root finding in Python, let us open up the Jupyter notebook with gaps for the parachutist and find the drag coefficient for a 70 kilogram parachutist to reach a velocity of 40 meters per second in 10 seconds. And then I'm asking you find the drag coefficient for a velocity of 10 meters per second. Okay, so let's go ahead and open up our Jupyter notebook. Okay, this is the parachutist example with gaps. Okay, so let's maybe increase the font size a little bit. And I'm starting by importing a bunch of things. Over here, let's restart this. And import NumPy. You will learn what this means in a second. The SciPy optimize, that's the built-in nonlinear solver. We'll look at that in a second. And just a basic boilerplate, and I have over here a description of what we're trying to solve. Okay, now the first thing we want to do is define the residual function for the parachutist, and in this case we're using m0, u0, and t0 in the function. Those will be defined later. So remember here r of c, let me fix this actually. R of c, that's the residual function, is we're trying to find the root c of this residual function, and we're assuming that we know m, g, and t, and u. Those are going to be given to you. Okay. Now in the implementation of this function, define R of c, so c is the only unknown in this R, and I'm assuming that I know m, g, t, and u, and that's why I'm calling those m0 and t0 and u0. Those will be defined later. So let's just define this function. Okay. Now let's plot it just to see kind of what it looks like for m0 equals 70 kilograms, t0 equal 10 seconds, and u0 equal 40 seconds. So what I have here, I'm defining a linear space x. This is really just the drag coefficient. So I'm going to plot this residual as a function of the drag coefficient because that's the only thing we don't know. I'm going to set m0 to 70, t0 to 10, and u0 to 40. Those are going to automatically translate into this function over here, okay, because they're not defined as parameters, so they're assumed to be global. Okay, and then we're going to plot the residual function as a function of the drag coefficient, various values of the drag coefficient. And if you go ahead and plot this, this is what you get. You get this nice decreasing curve, and it hits the axis y equals 0 right around this point. So on the x-axis we have the drag coefficient, on the y-axis we have this residual function, and this is our point, r of x or r of c equal to 0. This gives us the root or the drag coefficient for which a 70 kilogram parachutist will reach 40 meters per second in 10 seconds. Okay. All right, so activity 1 is to apply the bisection method, and I already have this programmed in here for you, so let's go ahead and define it. And this takes a function, a, b, tolerance, and maximum iterations. Now find the drag coefficient required for our parachutist, and we already defined m0 and t0, and we want to make sure that u0 is 40 meters per second. So we're going to call the bisection algorithm. Take a minute to figure this out. So looking at the bisection function, bisection routine, we need f. So what is f in this case is going to be our residual function. Now we need to bracket the root. So let's pick maybe 10 and 20 as our brackets. So let's do 10 and 20 because we know the root is located between drag coefficient 10 and drag coefficient 20. And then next we need a tolerance, let's say 1e to the minus 5. And let's put in 100 iterations for the maximum number of iterations. If you press Shift Enter, this is going to return, the function is going to return the root, the error, and the number of iterations it took to find the root. So, and it gave us 15.21 as the drag coefficient to achieve 40 meters per second. So we could home in better at the root. So let's say we take 13 and 16. And what do we expect here is to have less iterations to converge because we're closer to the root. And indeed, we get to the root in 17 iterations for the same error. Okay, and you can do better. You can go from 15 to 16, and that didn't make it much big of a difference. Now find the drag coefficient for a velocity of 10 meters per second. And I'm asking you here before you run this, do you expect the drag coefficient to be larger or smaller? So think of this for a second. For the same parachutist, 70 kilograms, and after 10 seconds to reach 40 meters per second, the drag coefficient was 15. Now to reach 10 meters per second, so that's a much lower velocity, do we expect the drag coefficient to be higher or lower? We definitely expect it to be higher because we're trying to slow down the parachutist within the same amount of time. That's 10 seconds. So we expect to have a lot of drag on the parachutist. And indeed, we do expect that the drag coefficient be higher. But first, let's try this. So u0 equal 10 and bisect, let's call it r. And let's try 15, 16, 1e to the minus 5, 100. If you run this, you don't get anywhere. You have very large error. The root is stuck at 16, and do 100 iterations doesn't do any good. If you do 1,000 iterations, doesn't do any good. The reason is that actually our bracket is wrong. So let's see how this works. So we're going to plot now for u0 equal 10 meters per second. Let's plot x and r of x or r of c, and let's see what happens. So this is going to intersect the y equals 0 line at about 65, at a drag coefficient of about 65 or 70 even. Okay, and our bracket, therefore, 15, 16 is a really bad bracket. So it looks like we screwed up the bracket. So we need to do a better job with the bracketing, and that's the challenge with these closed domain methods, and specifically bisection methods. So let's call the bisection algorithm again with different brackets. Let's call R, so bisect r, and let's do, say, 60 and 80, and 1e to the minus 5 with 100 iterations. Bam, there you go. You get the root 68.666, an ominous number. But you see how once you bracket the root, you can home in very, very quickly. So we can do, for example, 68 and 70, and we can do this with 13 iterations. Now, indeed, as we expected, that the drag coefficient be much, much higher than before, about 4.5 times higher to get to the velocity of 10 meters per second as compared to the velocity of the 40 meters per second. Okay, now before we switch to another closed domain method, I want to show you how we find roots with Python. The simplest function you can call is called fsolve from scipy.optimize. So you go from scipy.optimize, import fsolve, and then you call fsolve, you give it a residual function, initial guess. It's as simple as that. So what I have here at the top of this document is I imported fsolve already from scipy.optimize. And then what I'm going to do, I'm going to call it over here. So I'm going to put u0 equal 10 and then call fsolve. What do I need to give it? The residual function, and give it a guess. Now, in this case, it doesn't matter what guess you give it because it's using some fancy methods, but it gives you a way to check whether your solution is correct or not. So if we go to E040, you get 15.214, just like we had before. And this completes the bisection method.